Hi. So in this video, we are going to discuss some practice questions which are related to magnetic field and which are in reference to the previous videos in this playlist. So we have a first question here. So there is a positively charged particle which is projected towards east and is deflected towards north. So such kind of questions has to be followed by some diagrams, so as to understand it well. So say for example, there is a I'll just draw the diagram. And so, for example, this is the eastern direction and this is the northern direction. And as usual, as we know, this is the west and the south directions. So they are saying that, I'll use another color. Yeah, so they are saying that the positively charged particle is projected towards east. So that means it is projected in this direction and is deflected towards north. So it moves and it's deflected towards the northern direction. So the field may be as in they are asking that where exactly will be the magnetic field. And so for this we will have to use the Fleming's left hand rule. So these MCQs are mainly based on Fleming's left hand rule. And in Fleming's left hand rule, there is actually I cannot draw the diagram of the fingers, but if you take your left hand, then this is the thumb and this is the thumb. I'll just write down the short initials for just our understanding. And this is the first finger, that is the forefinger. So forefinger is indicating the direction of the magnetic field, and the line perpendicular to that indicates the direction of the current, that is the middle finger. So this is our Fleming's left hand rule, and probably we will be applying the left hand rule here in this case. So they are saying that the direction of current. So since the charge is moving, so say for example this is the charge movement which is in eastern direction. So in the direction perpendicular to that, as per Fleming's left hand rule, here is going to be the magnetic field. So this is the magnetic field. So in the three-dimensional system, so these two things like current and the magnetic field, they are in perpendicular direction. So in the direction perpendicular to that, as per the Fleming's rule, is going to be the force. So here the only option, the only place where it will be perpendicular is going to be this specific direction. So technically, if we see, so here it's going to be in the downward direction. This is where the force will be directed. So hence the correct answer for this question is going to be downwards. The field will be directed in the downward direction. So hence it's going to be downward. So moreover, if we direct this particular, this middle finger in the eastern direction as per Fleming's rule, then we can also find out that the magnetic field is going to be in the, in the downward direction. So you need to do that. You need to imagine that, and hence the question downwards. I mean, the answer downwards seems to be legit. Okay, we'll move towards the next question. Let me just copying the next question on the whiteboard. Okay, so this is the next question. So okay, so the question that is given to us here is a charged particle is whirled in the horizontal direction on a frictionless table attached by it to a string fixed at one point. The magnetic field is switched in the vertical direction. And so what will be the tension in the string? So now, first of all, they are saying that there's a horizontal circle. So a horizontal circle is, say, it is like this, and this is on a frictionless table, and the magnetic field is switched on in the vertical direction. So say for example, this is the vertical direction of the field, and here is where we are writing B. So this is the vertical direction. And so if we see as per the Fleming's left hand rule, I'll flash the image of Fleming's left hand rule, and you can see that for your reference in a while. So so as per the Fleming's left hand rule, I'll just keep that as a reference over here. So this is B, I mean F, and then B, and then I. So here, so this is the middle finger, then this is the forefinger, and this is going to be the thumb. Okay, so now yeah, so we will be using this idea here and we'll be solving this question. So basically, when the particle is moved in the horizontal direction at any moment, the current can be taken along the tangent of the line. So here you can say that this could be the direction of the current, like this. So it's somewhat like this. This is the direction of current, somewhat. Or yeah, so magnetic field is in vertical direction. So as per the Fleming's left hand rule, the force can be radially outward or inward. So that's how we can say that maybe this is the velocity and this is going to be the force. This is the velocity and this is going to be the force. So F is perpendicular to the velocity here. So yes, so depending on the direction of magnetic field, so force can be either outwards or force can be either inwards. So direction of the force depends on the direction of the wall. So we need to see that whether this is going clockwise or anti-clockwise. So here the correct answer is the tension in the string may increase or decrease. So basically tension is the force only. So it all depends on the force, that is clockwise or anti-clockwise force. So the correct answer to this question is going to be, it is the force may increase or decrease. Okay, we'll be moving towards the next question. Fine, I'll be just pasting it on the whiteboard. Okay, so here is the question. Fine. So in this question, which of the following particles will experience the maximum magnetic force when projected with the same velocity perpendicular to the magnetic field? So here we want to know that which particle experiences the, uh, which particle experiences the maximum magnetic force. So basically, here the magnetic force, the expression for the magnetic force is going to be Q. I mean, yeah, F is equals to QVB sin theta. Okay, so here we can see that the we can clearly see that the force, it depends on the charge over here. Okay, the charge here, only variation you can see electron, proton, He plus and Li plus plus. Like you can see that the charges for all are different. So it depends on the charge, I guess. So F is proportional to Q over here. Like if we consider V and B to be constant, okay, and theta to be constant, like V and B is perpendicular, so theta is going to be 90, right? So F is proportional to Q. So Q is maximum for lithium, I think. It is plus plus. That means it's +2 charge. So that's why the force here will be maximum for lithium. So answer to this question is going to be lithium. Okay, moving to the next question. I'll just paste the next question. Okay. Okay, so this is the next question here. And it says that which of the following particles will describe the smallest circle projected with the same velocity perpendicular to the magnetic field? Okay, and so for that, okay, so here we can see whenever the particle moves in the smallest circle, the magnetic field or the magnetic force will be same as the centripetal force. So I'll just write down as a solution that, just for the understanding, that magnetic force is equal to the centripetal force, and then we will be equating those equations. So I'll be writing and that is qvb. Yeah. So QVB is equals to mv square upon r, which is the expression for centripetal force. So it's going to be QV is equals to mv upon r. And here we are concerned with the radius. Smaller is the radius, smaller is the circle. So r is equals to mv upon qb. Okay, now if we consider that all other parameters are constant over here, like velocity, then charge, and then magnetic field, if all these things are constant, because you can see that in all of these options, the charge is -1 or +1, +1, +1, right? So charge is constant for all these options. So from that we can identify that r is proportional to m. So now if we see, we want the smallest radius, because they have said that which particle will describe the smallest circle. So that means smallest radius. Now radius is dependent on mass. So if you see lithium, helium, and proton, so out of that, an electron has the most negligible mass. The mass of the electron is 9.1 into 10 raised to minus 31 kilograms. So that is the negligible mass, and so that's why um electron is the correct answer for this question. Okay, we'll be moving to the next question. We'll be pasting the next question. Okay, so this is the next question. Fine. So which of the following particles will have the minimum frequency of revolution when projected with the same velocity perpendicular to a magnetic field? Okay, so here if we refer to the previous videos, then we sort of came across the expression for velocity, like synchrotron frequency is what I happened to discuss in my previous video. You should check out the playlist, and you will find out that the frequency is given by, okay, the frequency is given by, you can express it as frequency, that is mu, sorry. Yeah. This is expressed as nu is equals to 1 upon t. 1 upon t is equals to qb upon 2 pi m. So this is the frequency that, that is there. So now, okay, so here you can see in the options that charge on all the four particles is same. But you can also see that the frequency here is proportional, inversely proportional to mass. So if you see, in out of all these options, lithium has the maximum mass. So that's why the frequency will be minimum. So if mass is more for any charged particle, then the frequency of it is going to be less. So the frequency is going to be less if the mass is more. So that's why the answer to this question is going to be lithium, as its mass is maximum out of all. So if lithium was replaced with, say, let's say another option, that is, say, um beryllium, for example, if we had the ion of beryllium, then that would have been the answer. So out of all these four charged particles, I mean, the lithium ion would have the minimum frequency of revolution, you know. So yes. Okay, we'll move to the next question. Okay, so this is the next question. That is, a circular loop of area 1 centimeter square carrying current of 10 ampere is placed in the magnetic field of zero point 0.1 Tesla perpendicular to the plane of the loop. The torque on the loop due to the magnetic field is. So we just want to calculate the torque over here. So normally we should always write the data or the the information related to the question. But you see here, there's a circular loop and it is experiencing the uniform magnetic field. How do we know that it's a uniform magnetic field? They have clearly stated that the magnetic field is zero point 0.1 Tesla. So there's a uniform magnetic field, and so in such case the torque experienced is going to be zero, because since it is the uniform magnetic field, the here the net torque, like the net torque on the loop is going to be zero, since the forces will be in the opposite direction. So for any circular loop which is placed in a uniform magnetic field, it always experiences the zero torque, as the forces that exist in pairs, they happen to cancel. Sorry, I haven't copied the options here. So yes, I'll just copy the options for you all, and we'll conclude that the answer to this question is going to be zero. So yeah, just a moment. Okay. Yeah. So the answer to this question is going to be zero. So yeah, the answer. So yeah, the answer is going to be zero. Okay, so I'll be moving to the next question, and I'll be pasting the next question. So yes. Okay, so this is the next question. A beam consisting of protons and electrons is moving at the same speed. It goes through the thin region in which there is a magnetic field perpendicular to the beam. So the protons and electrons, what will happen to the protons and electrons? Well, we can clearly see that the protons and here protons and electrons. There's a beam. Beam as in it is a rod kind of object, and it has. We can clearly see that the force on electron. I'll just write down force on the electron. So, in such case, the force experienced by the electron is going to be F is equals to minus EVB. And the force on the proton, force on the proton. So, force on the proton is going to be F is equals to E. I mean, it won't be E because it's not an electron, right? So, it's going to be QVB. So, F is equals to QVB here. So now we can see that the magnitude is almost going to be same. It's just that the sign is going to be different. So now force is a vector quantity. So it's okay if we write here. If we write Q, then that is also okay. So minus QVB and plus QVB. So if we take the if we take the resultant, like if we call this as F1 and F2, so if we add them, so it's anyway going to be in the different directions actually. So that's why the answer to this question is going to be, they will be deviated at different angles, because they are two opposite charges, and so they will undergo the repulsion. So they will be deviated at different angles and will separate. They cannot stay in the same angle, right? They will deviate at different angles, and which clearly we can see from these signs, since the forces are in different directions. So the answer to this question is going to be C, that is deviated by different angles and will separate. So yeah. Okay, now we'll be pasting the next question. I mean, it's an interesting question, one interesting question. Okay, so yes. Okay, so we'll be just reading the question. A charged particle moves in a uniform magnetic field. The velocity of the particle at some instant makes the acute angle with the magnetic field B, and the path of the particle will be. Okay, so there is an acute angle involved. So there's a charged particle that is moving in the magnetic field B, and the velocity makes an acute angle with the magnetic field. So, here, so there is this diagram which is given to us. So, magnetic field does not change the direction, does not change the speed of the particle, rather, it changes the direction of the velocity. So, here we can say that mm, whenever there is an acute angle, so this is the velocity here, and there's a acute angle between the magnetic field and the means the angle is less than 90, so it will have the helix path, which is you know in the uniform helix path with the uniform pitch. So theta parallel to the magnetic field and V sine theta is perpendicular to the magnetic field. So magnetic field, it does not change the particle's speed, but it changes the direction of its velocity. So if the magnetic force acts on the particle due to vertical component of the velocity, which tries to move the particle in circle, and this force tries to rotate the particle in circle. But then there is a horizontal component of velocity, which will try to move the particle helically, with a constant pitch, because no force acts on the particle along the direction of the horizontal component of the velocity. So hence the correct answer for this is going to be, it will have the helix with the uniform pitch. So yes, I'll be copying the next question. So it is the same kind of question, and let's see that how to solve it. Okay, so yeah. So it is given as a particle moves in a region with the uniform magnetic field and a parallel uniform electric field. So now here both the fields are involved. That is electric field and magnetic field. So at some instant, velocity of the particle is perpendicular to the field direction. So if we consider the total Lorentz force, so whenever both the both the fields are involved, at that time we consider the total Lorentz force. So total Lorentz force, which can be indicated by F. So if we indicate that as if we indicate that as F, so F is equals to QE plus QVB. It's going to be QE plus QVB. So here we can see that magnetic field B does not change the speed of the particle, but changes its direction. So this B, it has nothing to do with the speed of the particle, but it changes the direction. But as an electric field is also present, it will accelerate the particle in the direction of the field, and so it will again be helix, but this time it's going to be in a non-uniform pitch. It will not have a uniform pitch movement just as it was there in this particular case. It will be the particle moving in the non-uniform helix pitch. So that's why the option D is the answer for this specific question. Okay, and I think probably I'll be doing the last question of the video here. And yeah, so I'll be just pasting the question. And yeah, I also have to make some changes in the options here. So okay, so I'm ready with the question and its options. So yes, yeah, I'll just check it from my reference book here. Okay. Okay, so the question says that an electric current I enters and leaves the uniform circular wire with the radius A. So say for example, this is the wire and its radius is A. Okay, and diametrically through the opposite points, a charged particle Q is moving along the axis of the circular wire, passes through its center at speed v. The magnetic field acting on the particle when it passes through the center has the magnitude equal to, what will be the magnitude? So here we can use the right hand thumb rule to get the direction of the magnetic field due to the current carrying wire. So, in the right hand thumb rule, you always need to, imagine this so that you can easily solve. So, we can say that the direction of the magnetic field is along the axis of the wire, and the charged particle is also moving along the axis of the wire. So, no magnetic force will act on it, as the angle between the magnetic field and and the velocity is going to be 0. So let me just determine the axis first of all. So yeah, the axis should be, I think axis should be like this. So if I redraw this, then this should be the axis. So they are saying that the So yeah, here we can say that the magnetic field, that is magnetic field B, and the velocity, mm, of the charged particle velocity. So there is a charged particle which leaves and enters at the diametrically opposite points. So the speed and the the velocity and the magnetic field will be probably in the same direction in this case. So that's why the angle between them is going to be either 0 or 180 degrees. So that is why the force which acts on this particular particle, as per F is equals to QVB sine theta, QVB sine theta. So, and that is going to give us QVB sine 0, QVB sine 0. So that's going to give us 0. So the force acting on this is going to be 0, So yes. So I think this is it. See you in the next video. Thank you. Bye.